go. Inverse functions. Inverse functions, I think that conceptually it's kind of difficult sometimes to get to wrap ourselves around it. In the end, what you're asked to know about it at this level is not really that much. I don't want to just fall back on, well, this is all the SOL is going to ask you. But in a way, I do want you to feel comfortable that you're not going to get asked to do something that is at a level above what we're doing in this class right now. But you want to have a good foundation in this, because when you get to math analysis, they do more with this. If you go in not having, my guess right now is that not just you guys, but the 4 algebra 2 trig classes that I've got this year, you're doing very well when it comes to things like domain. Some of you may be going, what's he talking about? But it does seem to me like you're doing pretty well. And that's really going to help you when you get to the next level. It really, really will. Inverses, we're going to give you, what you need to succeed for this year, and then hopefully getting into the next class. These things right here, this is specifically the knowledge and skills that it says we're supposed to have from our standards. We're supposed to use composition of functions to verify 2 functions or inverses, okay? That's why we do compositions, and the next day we do inverses. It's because we're going to use compositions now. Where obviously we'll find the inverse of a function, and then we will understand that a function and its inverse, if they're graphed, they look like they are reflections across the line y equals x. Okay, so those are the 3 specifics that we're supposed to focus on. So if a function has an inverse, and they don't all have inverses, and we'll talk about when they do and when they don't, but if they have an inverse, then if you take the composition of the function and its inverse, they cancel each other out. So if f of x and g of x are inverses of each other, then f of g of x equals x. And g of f of x, flip the order, it's still, everything will cancel, and all you're left with is x. All you're left with is whatever's in parentheses. Okay. If g of x is the inverse of f of x, then we have a notation for that. And it is right here. Okay, let me give a pointer. Right here. F with a superscript of -1 of x. F to the -1 of x. That's how you write the inverse. And that -1, it's not an exponent. Right? It's just how we write the inverse of a function. Let's see if I can get away with this. If you look on the calculator, on the left side, in the middle, there's an x to the -1 button there. X to -1. That's not an inverse function, right? That's not a key that you can put in a function and then hit that and it gives you the inverse. That's not it. That's saying 1 over. That's like flipping something to the other side of the fraction. That's all that is. But in fact, there is, on the front of your calculator, there are inverse functions, and you've actually used them before. What are they? Yeah, look at the sine, cosine, and tangent, and then what is right above them. In my calculator, it's in blue. I don't know if yours are in blue. Sine -1, cosine -1, tan -1. You use those. Do you remember when you're doing right triangle trigonometry that sometimes you had to use those functions right there? You're supposed to have used them. Right? Here's an example of how you used them then. Okay, you had a right triangle. It was not one of those 30, 60, 90, 45, 45, 90. So you had to solve for the x. And if you remember this, right? First you look at the triangle and you say, with respect to that angle, which I've got at x degrees there, the 2 sides that are marked, one is 23 and one is 34, we can call opposite, adjacent, or hypotenuse. Which are the 2 sides that I'm looking at there? What is 23? The side that's marked 23, what would you call that? Opposite, right? If the angle is here, 23 is opposite. What does that make 34? hypotenuse, right? That's the hypotenuse across from the 90. So you would say, okay, this is opposite. Oops, turn that off. This is opposite. This is hypotenuse. So then you would go to something like this, SOHCAHTOA, and you would say, okay, well, which one of our three trig functions uses opposite and hypotenuse? Right? It would be sine equals opposite over hypotenuse, right? So we would use that and say sine of x equals 23 over 34. Okay, well now we have to solve for x, and x is inside of the trig function. So in order to isolate the x, I can't divide by sin. Okay, that doesn't work. This is what you really do, right? But you probably didn't show this when you were doing this in geometry. In fact, you do sine inverse of sine of x equals sine inverse of 23 over 34. You take the sine inverse of both sides, right? It's still algebra, so if I do it to one side, I got to do it to the other side. Okay, but this right here, the sine inverse of the sine, that's a composition. That is, we're just putting one function into the other, so that's the composition. And if you go back to the slide before, you know, what should we get when we take the composition of a function of its inverse? You're going to get the x. So in a way, that does isolate the x. So now we can say that x equals sine inverse of 23 over 24. And that you put in the calculator, just use the second, sine 23 over 24. Make sure you're in the correct mode, because it's probably set to radian mode and you need it to be in degree mode. And you know, we don't really care about the answer here. I'm just trying to like make sure we remember it. You've used inverse functions before. I mean, kind of the way that this works is, if you know what the sine, you know, we know how to plug things in for the sine. Imagine that you could just, for all values of x, you could just like fill up a table where you say, sine of this angle is this, and sine of that angle is that. And you could do it to the 10th of the degree and the 100th degree, and you have this big table. So now if you say, what's the sine inverse? It's like you go into that big table of data, and wherever you find the value there, then you go back and say, okay, well then the angle must have been that. It's kind of like a reverse lookup when you do the sine inverse. So inverse functions allow us to solve what you call transcendental functions. These are functions that they're not just some combination of polynomials that could either be, the variable can be isolated by doing operations to both sides, or maybe they could be factored, and then you could take each factor and set it equal to 0, right? That would be that's solving algebraically. And you can do that with non-transcendental functions. But transcendental means things like trigonometric, sine, cosine, tangent, exponentials, and logarithms. Those we're never going to be able to just like isolate by doing operations to both sides. We need some other trick to do it. And that's what inverse functions do for us. Yeah, we'll do the exponentials and logarithms for the next 2 lessons. We don't go like deep into it. In fact, our main interest in exponentials and logarithms are really just to support this concept of inverses and some of the function stuff like domain and range and things like that. You do a lot more with exponentials and logs next year. So, I'm not completely thrilled with this, but I mean the one point that this gets across, if you define the inverse, whether it's a set of points like this is, or whether it's actually a function with an equation. You find the inverse by swapping the domain and the range. Swapping the x and the y. That's how you find an inverse. Generally speaking, that's how you find an inverse. So if you notice the blue table of values there, that's a set of 5 points. For f minus 1 of x in purple, I've just switched all the x's and the y's. That's the inverse. Okay, notice the first point. So in the function, f of 0 equals 6. Well, what point is that? If x equals 0, then what point is that? It's the y-intercept. It's 6. But if I flip them, right, now what point is that? It's the x-intercept. Okay, the other point's the same. So 1, 4 would be 1, 4 is there. 2, 2 is there. 3, 0 is there. 4, negative 2, I didn't draw this quite far enough, but it's be about right there. Okay, I'll plot the other points now. 6, 0, 4, 1, 2, 2, 0, 3, and negative 2, 4, like right there. Now, normally, if you're given a set of points, you don't assume that they mean that you're supposed to connect them all, but I'm going to connect them just because it makes what we're supposed to understand about the graph look better. So let me do this. Get a dashed line in purple. That is, don't like that. That's close enough. Blue. Like that. Okay, and now the last one, red, but I'm going to make this a solid line. So if that's the graph of the function and its inverse, they should look like they are reflections across the line y equals x. And y equals x is this line right there. Right? 1, 1, 2, 2, 3, 3. Okay, do they look like they're reflections across that line? I'm going to walk away from the microphone here. That. That, okay, that is y equals x, the intended function, right? Because every x and y didn't draw very well. 1, 2, 2, 3, 4. Actually, I really messed that up. That should have been like that. Now it looks a little bit better. Let me show you something. This is a test question. This is from a released SOL from a few years ago. Okay, it says, here's the function right here. Okay, which one of these is the inverse? Okay, so the only thing you need to do is pick a couple points on the original function, switch the x and the y, and see which one has those. So let's say, because the easiest 2 points would be to look for the x and the y-intercept. So let's say this one has a y-intercept of 0, 2. So which one of these has an x-intercept of 2, 0? Well, C does and D does, right? Okay, how about the x-intercept of the function is 4, 0. So which one of these has a y-intercept of 0, 4? C. So the right answer is C. That's the whole question. And they have like 2 questions on inverses on the SOL. And that is likely to be pretty similar to the one you're going to see. All you got to remember is switch the x and the y, and then which ones match up. Okay. So the graphs of a function and its inverse are reflections of each other across the line y equals x. Right? That is one of almost word for word the SOL says that's what we're supposed to know. Okay. So now here's how, if you have a function, you have to find the inverse. right? These are the steps. Replace f of x with y. Now, sometimes when you're given the function, it's y equals, so you don't have to do that step. But if it does start with f of x, then replace the f of x with a y. Okay. Then swap the x and y. Just change positions. Okay. Now that y will not be isolated anymore, so isolate it. Solve for y. And then when you've solved for y, that will be the inverse. So you can replace the y with f to the minus 1 x. So like as an example for this problem right here. Okay, first I replace the f of x with a y. Blue. Y equals 3x minus 5. That's step 1. Step 2. X equals 3y minus 5. That's the swapping. Solve for y. Add 5. Divide by 3. And you could split that up into x over 3 plus 5 over 3 or just leave it alone. It doesn't matter. F to the minus 1 of x equals x plus 5 over 3. Those aren't typically for guys like you. That's not going to be that hard of a process to do it. Typically, the kind of question you get is a multiple choice question says, here's a function, which one of these four is the inverse? What I like to do on a problem like that is I don't even find the inverse. I just pick a value of x. For example, if I say up here, if I find f of 2, what do I get? If f of x is 3x minus 5, then f of 2 is 1. 6 minus 5 is 1. Okay, well then it should be the case down here. If I find f to the minus 1 of 1, I should get 2. So let's do that. What is f to the minus 1 of 1? Okay, well that'll be 1 plus 5 over 3, which is 2. Okay, so that's the inverse. So if I have 4 multiple choice answers, that's what I do. Quicker than finding the inverse, actually, is just pick a value, find what f of x equals, and then take that value, put it into the inverse, and see which one gets you back with what you started. And that is typically one of the questions. If you get 2, that'll be one of them. So just to practice this process, try to find the inverse of that. Minus 4 makes sense, right? Y equals x plus 4. X equals y plus 4. Solve for y. Y equals x minus 4. F to the minus 1 of x equals x minus 4. Again, what is f of 0? Equals 4. Okay, what is f minus 1 of 4? Put in 4 right there. 4 minus 4 is 0. Okay, that's how it's supposed to work, right? The function takes you from this way, the inverse takes you backwards. Okay, so the next thing, this is an SOL. Verify the two functions are inverses. Okay, if they're inverses, then we should be able to take the compositions f of g of x and g of f of x, and they should cancel each other, and all you have left is x. So I'll do this one, and then there'll be a you try. So f of g of x, f of g of x. Okay, again, that's why we do compositions right before we do inverses. That should be 2 times x over 2 plus 1/2 minus 1, right, which is x plus 1 minus 1, which is x. Okay, now that's not sufficient. It's not sufficient just to do one of them and show that it works. You've got to do both of them. So now I got to do g of f of x. Okay, so g of f of x, now I've got to take this and put it into that. So that'll be 2x minus 1 over 2 plus 1/2, right, which is 2x over 2 minus 1 over 2 plus 1/2, which is x. Okay, so both of them equaled x. That is the confirmation that these are inverses. Good. Good. Okay. So try to verify those two. Okay, x. Anybody have any trouble doing that? Putting one inside the other. Simplify. Takes a little bit of algebra. Okay. Okay. Find the inverse. So what we've done up to now is linear. Those are both linear. This is quadratic. So let's see how that works. So first, f, put it, substitute y. Okay, why is that not going? Don't start to fail me now. Sometimes I just have to like unscrew this. What caused that to all of a sudden stop?